Oh, hi, this is Carly McAvoy. I'm doing homework 4A for statistics. Hope you're having a great day and looking forward to doing a little math. Question number 1 here, if A denotes some event, what does, with the little bar above it, A mean, which is A prime, or the complement of A? So what does it mean? It means everything that's not A. So if you had a group of people and you looked at people that were between the age of 12 and 18, and then you said everybody else is the complement of A, it's everybody who's not between 12 and 18, then you're the rest of the group. So this event denotes the complement of A, meaning that the complement of A consists of all outcomes in which A does not occur. So it's the outcomes in the sample space that aren't A, anything else. And so then they give us a value of 0.992 and ask what's the value of the complement of A if A is 0.992. Well, 2 events that are complementary make up the entire sample space, and the sample space adds up to 1. So in order to figure out what the rest of the sample space is, you just take 1 minus that. So I'm going to do that without showing you because I feel pretty confident you could all do that on your calculator. 1 minus 0.992. And that gives me 0.008. And that's going to be the complement, and those 2 things add up. Is the probability A, is it unusual? Is A prime unusual? When we talk about unusual events, we talk about 95% would be usual, and if it's outside of that, that is at 5% or less, we say that it's unusual. And since this is 0.008, that's 0.8%, which is unusual. So the complement is unusual. It doesn't happen very often. Most people fall into the A event, it looks like. Okay, which of the following cannot be probabilities? Cannot be probabilities. Probabilities are not negative. You can have a probability as low as 0 and as great as 1, but you can't have more than 1, so forget about 5/3. You can't have 1.22 because that's more than 1. And it's not irrational. I'm going to just see, yeah, we can't put an irrational number in there, so the square root of 2 doesn't make sense either. It could be as low as 0, as high as 1. It could be anything between there. This is 0.6 if we change it. So there's all the possibilities. If you took the square root of 2 and then you rounded it, you could get a probability, but I guess they're saying if it's exactly the square root of 2, it can't be an irrational number. So, okay. 7 of the 50 digital video recorders in an inventory are known to be defective. What is the probability you randomly select an item that is not defective? So if we take, let's do my problem. It's a little different than that one, but I've got it typed up down here so we can look at it. So let's switch over to my paper. Sorry, I didn't do this earlier. I like to have here. Okay, so this is number 3. This one says 20 of the 100 digital video recorders in an inventory are known to be defective. What is the probability you randomly select, we can see 0.8, but you randomly select an item that is not defective. So if we have 100 total and we know that 20 of them are defective, then we know that 80 are not defective. So if you think about it, in a dish or whatever, in an inventory shelf or whatever, you have 100 items, 80 are not defective. Then if we reach in and choose and we don't want defective items, we have 80 out of 100 chance that we're going to get not defective item. We have 20 out of 100 chance to get a defective item, but they're asking us what's the probability that it would not be defective. 80 out of 100 is 0.8 as a decimal. So 0.8 chance that our item would not be defective. All right, let's see what number 4 is. Maybe we don't have to flip back to that. All right, assume that 700 births are randomly selected and exactly 167 of the births are girls. Use subjective judgment to determine whether the given outcome is unlikely, and also determine whether it is unusual in the sense that the result is far from what is typically expected. Okay, so when you want to know when you're talking about births, I mean, you're always wanted to say that there's a 50% chance of having a girl and a 50% chance of having a boy. People argue that sometimes, but statistically it shows that that's the truth. And so when we want to figure out, well, what was the probability of our little example here, we take the possible births, 700, and we put that under the total actual births of girls. So we had 167 out of 700 births that were girls. So if I do 167 divided by 700, I get 0.238. I'm going to call that about 0.24, just rounding it, because the question's not really, it's asking me to make a subjective judgment. So I'm saying, okay, it looks about like 24%. Okay, so I'm looking at 24%. So if it was 50%, we would expect 350 girls. This is definitely not normal, right? It could be happening on one day that happens, but it would be really, really unusual for that to happen because we should be closer to 50%. Now, if we were at 39%, that'd be pretty low, but like possible. If we were at 55%, good. But we're not going to be exactly 50, but we should be in the ballpark of 50. So it is unlikely, I think. It is unlikely because it is not 350 as expected. That could be an answer. It is unlikely because there are many other possible outcomes that have similar. No, that doesn't even make sense. It is not unlikely. It is about a quarter, but that's unusual because it should be 50%. So it is unlikely because it is not 350 as expected. Where's the 350 come from? Well, half of 700. That's about what we would expect. Determine whether exactly 167 girls out of 700 randomly selected births is unusual. It is unusual because, wait a second. Well, I think this was a bad rap. I mean, now that I'm reading this again, I don't like it. It's true, we would expect 350. We don't really want exactly 350, though. That's what makes that question a little funky, right? So I would say, as I'm thinking about this, I didn't even finish reading this, and now I'm looking back. Obviously, it's not these that are too unlikely. It is unlikely, so it's one of these two, and it must be this one. And let's read through this a little slower where I kind of gave up on it because it sounded strange. It is unlikely because there are many other possible outcomes that have similar or higher probabilities. Okay, I don't know what they're trying to say there, but I don't like this one, so I think it is C. There are many other possible outcomes, like you could have 250 girls, or you have 275 girls, or whatever, but they would have higher probabilities, and so we would be more likely to see something like 325 girls or 367 girls. So there are, I guess that's what they're saying, is there's many other possible outcomes, but those would have higher probabilities, I think. Okay. All right. So, and I'm going, and I know what the answer is, so it's trying to make sense. Determine whether 167 is unusual. Oh, here I was kind of answering the unusual question. It's unlikely. Okay. It's unlikely because it is unusual because it's small, right? It's a really small, 24% is an unusual occurrence. So I think this is the one that this is B, somehow didn't print out, but it's unusual because it's not about 350. I like the word about there that's not in that one, right? Because we don't expect it to be exactly. We expect it to be about that. So that's kind of a weird little question. I'm going to move on. Okay, for a certain casino machine, the odds in favor of a win are given as 77 to 23. Express the indicated degree of likelihood as a probability between 0 and 1 inclusive. Inclusive means could be 0, could be 1, something like that. Well, odds in favor, when you talk about odds in favor, you talk about the favorable outcomes over the unfavorable outcomes. Now, what is unfavorable and favorable to you might be different for somebody else. If you're the casino, when you lose, that's a favorable outcome to them, right? But for this particular one, we're going to say favorable is when you win. And odds in favor, and these two odds always add up to the sample space. Okay, so we have the odds in favor given first. So the favorable outcomes are 77 and the unfavorable outcomes are 23, which when you add 77 and 23 you get 100, right? So there's 100 in our sample space. Express the indicated degree of likelihood being that you would win as a probability between 0 and 1. So the probability that we win is 77 out of 100, or 77%. All right. So when you have that, it doesn't always have these two that add up to 100. So this one was particularly easy because they did, but they don't always. But you always want to add those up to see what you're dividing by, and then you're on top is your favorable outcomes. If they said odds against, then it would be different. And so odds against would be the unfavorable outcomes on the top and the favorable on the bottom, so it's a little different. Okay, you are certain to get a red card when selecting 27 cards from the shuffle deck. Why is that? Well, there's 52 cards and there's 26 black and there's 26 red. So it would be really, really unlikely for you to draw 26 cards and have them all be black, but it's possible. But when you draw the 27th card, it is no longer possible because you've used up all the black ones. You're going to have to get a red one. So that's what this is saying. You're certain to get a red card if you select 27 cards. That makes sense. Express the indicated degree of likelihood as a probability between 0 and 1. Well, it's going to happen. It has to happen. That's a certain event. When we say certain event, it's like 100% chance. And as a decimal, that's just 1. So 100% chance means yes, it's going to happen. You are going to draw a red card by the 27th card, and probably way before that, right? But that's a certain event. Okay, cool. All right, number 7. I'm going to just go through these on here. If there's something that seems like it'd be tricky to enter, I'll let you know. But remember that you want to always, when you're looking at the Math Excel program, that you want to read the directions about where to round or how many places to round to, right? Because that makes a difference. All right. Okay, so refer to the sample data for pre-employment drug screening shown below. If one of the subjects is randomly selected, what is the probability that the test result is a false positive? Who would suffer from a false positive result and why? Let's think about false positive. So you get tested because you want a job. They make you drug test. And you get shown to be positive when it's actually false. In other words, you weren't using any drugs, but your test showed up positive because you ate a poppy seed muffin or some crap like that. So who suffers from that? Well, if you're the person trying to get the job and you're told, yeah, you showed that you were positive for drugs, that's going to make you suffer, right? So not the employer. Maybe the employer, they missed out on you, which might have been their loss, but really the loss is going to be you. So these drug tests that have potential to be false, that's bad for people that are getting those false positives. Okay, that's the second part of that. But let's see. The first part is if one of the subjects is random, what is the probability that the test result is a false positive? Okay, so you want to round your answer to 3 places. Okay, just making sure there's the second part of that. Well, how many results are there altogether? How many people were actually screened here? We have 47, 28, and 36. So if I add all those together, I get 111 people that were tested. Okay, so I'm always wanting to find out what's my total sample space. Then I want to know how many of those people came up with false positives. So a positive test result, but the subject is not a drug user. This is a false positive, right? They tested as if they were positive for drugs, but they were not drug users. So there's 20 people out of 111 that happened to. That's your probability of being falsely positive divided by 111. 0.180 because they said to 3 places. That's going to be that. And then who would suffer? Well, the person tested would suffer because they would be suspected of using drugs when in reality they don't. So that's that. That would be, wait, the person is at risk. Yeah, it's, I read D really quick, but C is the one, right? You can figure that out. Okay. Let's look at number 8. Dun, dun, dun. Refer to the sample data for polygraph tests shown below. If one of the test subjects is randomly selected, what is the probability that the subject is not lying? Is the result close to the probability of 0.427 for a negative test result? Okay, I don't know what that's talking about. But anyways, we want to know the probability that the person was selected and was not lying. Okay, what are the total number of people that we're talking about here? 13 plus 38 plus 9 plus 29 is 89 people. So we have 89 people that we looked at. What is the probability that the subject is not lying? So the probability that they didn't lie, here it is. They just want to know how many people were not lying. Did not lie. Here we go. 13 and 29. 42. And 42 divided by 89 is 0.472. That's rounded to the 3 decimal places. Does everybody see where I got 42? I'm just adding these two to get 42. They're the people that did not lie. Okay, second question. Is the result close to the probability rounded to 3 decimal places of 0.427 for a negative test result? So if you look across this way, 29 and 9, that's a negative test result. Negative test result total up to 38. And 38 divided by 89 is apparently this Jimmy Jam. And they're saying, is the result close to the probability if you round to 3 places? So when they ask you if it's close or not, what you're looking for is this 0.05. They keep throwing that out there because it's important. If it's within 5% of the actual, we say it's close. Okay, and this one is 0.42 to 0.47 is 0.5, so it's actually close. So I would say B. They're all kind of the same. Yes, because there's less than 5% absolute difference in the probability of the true response and the probability of a negative test result. Yeah, so that's what we're looking for, though. If you subtract those, we should have a 0.5% or less. All right, so that's what that's about. And what they're saying is the test said that there were 42% people that weren't lying, but the actuality, the people who didn't lie was 47%. So those should be close. Like if your test is good, if it was perfect, those two numbers would be exactly the same, right? So they had some discrepancy. And I will give you advice for free right now. Not legal advice because I am not an attorney. Don't offer to take a lie detector until you have talked to your attorney. I know people who have taken a lie detector who were innocent, so they were like, sure, I'll do a lie detector. They got all nervous, and then the lie detector showed that they were lying, and then they can use that in court against you. So I'm just saying, don't do it even when you're innocent. Especially if you're innocent, don't do it. Talk to an attorney first before you make that choice. Okay. Number 9, in a test of gender selection technique, results consisted of 204 baby girls and 193 baby boys. Based on this result, what is the probability of a girl born to a couple using this technique? Does it appear that the technique is effective in increasing the likelihood that a baby will be a girl? So, well, we need to figure out how many babies there were in this little project. You see how there's more girls than boys. So that's good news if you're trying to have more girls, I guess. 397 total. We would expect 50% birth rate. So we're going to look at the girl is 204 divided by 397. And we got a birth rate of about 0.3 decimal places, 0.512. Okay. Does this technique appear, I didn't read that right, but does the technique appear effective in improving the likelihood of having a baby girl? Well, we expect about 50%, and this is higher, but not that much higher, because remember what we're looking for, and we talk about is it significantly different, is it 5%. It would have to be 55% or higher for us to start to consider if that's useful, our technique. So it sounds to me like no, it's not effective because it's only 1% different, which could happen by chance. If that kind of thing could happen by chance, then the method cannot be blamed. I know people who swear by those methods. I know people who have tried them and had failed by them. So that's how that works. I mean, they're not always effective, and we can't expect them to be. But so far, anyways, maybe they'll be better coming down the pipe here. All right, so it looks like to me that not really that effective. Okay, number 10. In a genetics experiment on peas, one sample of offspring contained 370 green peas and 33 yellow peas. Based on those results, estimate the probability of getting an offspring pea that is green. Is the result reasonably close to the value of 3/4, which was expected? 3/4 is 75% or 0.75. That's what we should see if it's actually close to that. So we need to figure out how many peas there were altogether, which means we're going to take 370 green, not that, and add the 33, and that gives us our sample space of 403. What is the probability of getting a pea that is green? Well, we have 370. I should turn my email off. That's a little annoying. 370 green peas divided by 403 total. And we get a probability 2-3 places of 0.918. The question is this probability reasonably close to 3/4? This is not reasonably close. Reasonably close is within 5%, right? This is from 75, 16% difference. So no, not reasonably close. All right. All right. The answers, yes, no. Okay, here we go. A test for marijuana usage was tried on 225 subjects who did not use marijuana. The test result was wrong 60 times. Based on the available results, find the probability of a wrong test for a person who does not use marijuana. So, we had 60 of those people. 60 divided by the sample space of 225. That's, do we want to go 3 places? I don't know. Yes. The probability the test will be wrong is 0.267, approximately. Is it unlikely for the test to be wrong for those not using marijuana? Choose the correct answer below. Is it unlikely? Not unlikely. It's pretty likely, right? When we want it to be unlikely, we say that 95% would be likely, and if it's 5% or less, that's unlikely. If it's more than 5%, we keep talking about that 5%, it's an important number in statistics. If it's happens more than 5%, it's not unusual, and this is a really crappy test, right? Because it's got 27% of the time it's wrong, right? That's not good. So is it unlikely? No, because it's more than 5%. Then it becomes usual or likely to happen. Okay, so 6 and Here we go. This was we just did number 11, so we're on to number 12. Okay, in a survey of consumers, well, there's the answer, but it doesn't matter. I can cover it up, but I want space to work here. In a survey of consumers aged 12 and older, respondents were asked how many cell phones were in use by the household. They weren't from the same house. Among the respondents, 205 answered none, 278 said 1, 365 said 2, blah, 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 blah. A survey respondent is selected at random. Find the probability that his or her household has 4 or more cell phones in use. Is it likely... Okay, that's the second question. Let's answer the first question. So how many people did they talk to altogether? That should be something that we're interested. 205 had one answer. 278 answered something else. 365 answered something else. 137 answered something else. 95 is the one we're looking for, 4 or more. We add that onto our sample space though. So it looks to me like we have a total of 1,080 respondents. Those are people who answered our survey. And of those, 95 responded with 4 or more cell phones. So 4 or more cell phones in use, that's 95. Probability of 4 or more cell phones is then 95 divided by 1,080, which is 0.088. Right? That's that rounded approximately to 3 places. Is it unlikely for a household to have 4 or more cell phones in use? Well, I'm going to let you answer that one on your own. But think about this. If it's more than 5%, it's not unlikely. So you got to find that. No, it's not unlikely. It's happening almost 9% of the time. That's not unusual, right? We have 5 on our plan, so I don't think it's all that unusual. Okay. Let's move on. You can answer that one. You'll have fun reading those 4 choices. Okay. To the right are the outcomes that are possible when a couple has 3 children. They could have a boy first, followed by 2 more boys. They could have a boy, boy, girl, boy, girl, boy, blah, 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 blah. If you have 3 kids in your family, you are one of these scenarios. That's the only thing you can have. Those are all the outcomes, right? You can have 3 girls, 3 boys, or combinations of each. What is the probability? Okay, so how many outcomes are there? There's 1, 2, 3, 4, 5, 6, 7, 8 outcomes. It turns out when there's only 2 possible outcomes, like having a boy or a girl, and you're doing 3 times, it'd be 2 to the 3rd. That tells us what our sample space is going to be 8. If you had 4 kids, it's 2 to the 4th, or 16 possible outcomes. If you had 5, it's 32 outcomes, and if you had 6 kids, you'd have 64 outcomes. In my family, we had 6 kids. And of those 6, 1 boy and 5 girls. That's kind of an unusual combination because you're more likely to have 3 and 3, or at least 2 and 4, something like that. You can think about how unusual your family is. Because it's supposed to be 50-50 each time you have a child. There's a book that has you probably could find it online if you Google it, but there's a woman that had 19 children, all boys, 19 boys. The probability of that happening is so astronomically unreal. It's 2 to the 19th power. What is 2 to the 19th power? 2 raised to the 19th power is 524,288. So it was a 1 in that. So 1 divided by that answer. There's, if you move it over 2 places, you have 1, 2, 3. Yeah. That's the percentage of chance that you would have of having that happen. So not very often, right? Very low probability, definitely unusual. Okay, but anyway, I digress. What is the probability of exactly 0 girls out of 3 children? Here, right here, is the only place where we have 0 girls. That's when we have 3 boys. And that happens 1 out of 8. 8 possibilities, 1 time there's no girls. What is the probability of exactly 3 girls out of 3 children? Well, there's 1 time when you get all 3 girls. That's down here. That's also then 1/8. What is the probability of exactly 2 boys? Now this is a little different. Exactly 2. We can't have 3, we can't have 1. Here's one with exactly 2. Here's one with exactly 2. And there should be another one in here. Here's one with exactly 2. So you could have a boy, 2 boys at the beginning, 2 boys at the end, or a boy on the beginning and end. Those are the 3 ways. So that gives us 3/8 ways to get 3 boys. And that page is fini. All right. Okay. A modified roulette wheel has 44 slots. One slot is 0 and another is 0, 0. And the others are numbered 1 through 42 respectively. You are placing a bet that the outcome is an odd number. 0 and 0, 0 are neither odd nor even. What is your probability of winning? So there's 44 slots, sorry. Right? And the probability of winning, well, out of 42, because we're not going to count 0 and 0, 0, those are just out, which means there's 42 other slots. Half of those, or 21 of those, would be odd, and the other half would be even. So you have 21 out of 42, an integer or a simplified fraction. So 21/44 is what they're looking for here. They don't want a decimal, so you just leave it that way. What are the actual odds against winning if you place that particular bet? So there's 21 times when you're going to win, but we're talking about odds against. So when odds against, we put the odds, the unfavorable outcomes, on the bottom. And there's 44 outcomes, right? So remember that these two numbers, when you're doing odds in favor, odds against, the number on top and the number on bottom add up to your total sample space, 44. So you're going to take your 44 minus the 21 times that you will win, and that's going to tell you that there's 23 times when you won't win. So odds against, 23 against, 21 in favor. So it's in the house's favor by adding the 0 and the 0, 0. Tricky, huh? If they had put it, just left it as normal, you'd have half a chance of winning, half of losing. But they have increased it, so now they have a little better chance. So that'd be 23 to 21. When you bet that the outcome is an odd number, the payoff odds are 1 to 1. So in other words, how much profit do you make if you bet $15 and win? You don't make any profit. The payoff, if you win, the payoff is $15, right? But it's how much profit do you make? Well, do you see, okay, so this is what they're saying. If you win, the payoff is 15, but you bet 15. 1 to 1 means whatever you pay, they're going to pay you back the same. You're not making any money. You won. You had a chance of losing, a better chance of losing, but you won, but you still didn't get anything. Oh, that's in the casino's favor, right? The question they're asking here is how much profit should you make on the bet, $15 bet, if you could somehow convince the casino to change its payoff odds so they are the same as the actual odds against winning. Well, if we took 23 divided by 21, I'm kind of going on a limb here because I don't know the answer to this, but I think this is what I would do. Instead of paying me $15, the 21, that should be about $1.10, right? So what I should get is $1.10 times my 15, or 1.09 times my $15 bet, and I would get $16.43 for that. Like I'd get, because these are the odds, is 1.095, or about that. I should change this to 1.095. So if I took 1.095 times the $15 that I bet, my payoff should be $16.43. Let's see what they have. Yeah, $16.43. So that's what they should be paying off if they were really being fair, because your odds of winning are not 1 to 1, but they're paying you off as if they are 1 to 1 to 1. So they are saving themselves $1.43 by changing those odds to not fair for you. I hope that's not coming as a surprise, that casinos are not set up to be fair to you. They're set up so that they win, and they all act happy when you win, but really they can be happy because they know overall everybody's going to lose and they're going to make money. Okay. That's that. Number 15, moving right along. I forget how many there are on this homework assignment. Let's check in. I don't want anything to shut down because I haven't been there. So let's see. We're on 26 questions and we're on number 15. All right. Determine whether the two events are disjoint for a single trial. Consider disjoint to be equivalent to separate or not overlapping. Randomly selecting a guitar from the instrument assembly line and getting one that is free of defects. Randomly selecting a guitar from the instrument assembly line and getting one with a warped neck. These are really hard for people. We want to know if they're can they occur at the same time. You go and pick up a guitar and get one free of defect. At the same time, could you pick up a guitar and have one that's wrapped, that's got a warped neck? No, because it can't be free of defects and warped at the same time. So they're two different, these are disjoint. They cannot occur at the same time. Oh, jeez Louise. What did I say? Oh, I said they can't. All right. I said it, but I didn't choose the right one because I was talking. Sometimes it's hard to talk and read. The events are disjoint because they cannot occur at the same time. I'm feeling confident that I'm going to get this one right. It makes sense to me because you can't go take a guitar off the line and have one be warped and at the same time no defects. I mean, it just doesn't make sense. So it has to be that they're disjoint. Okay, randomly selecting a statistics student and getting someone who brings a notebook to class. Randomly selecting a statistics student and getting someone who brings a calculator to class. Could you pick one person and at the same time have them bring a notebook and a calculator? You might be surprised at how hard that is. But it is possible, right? Because you could have somebody who brings both. So it's not disjoint sets. They're not disjoint. The first event can occur at the same time. They are not disjoint. They can occur simultaneously. Having a calculator, having a book, or whatever they said. Find the indicated complement. Remember, a complement of a set is what's left over when you take the other set away. The certain group of women has a 0.77% rate of green-red color blindness. If a woman is randomly selected, what is the probability that she does not have red-green color blindness? So this one I'm going to flip over to my paper just because I want to show you something that, this is something that people miss a lot. You end up getting it because you figure it out, but it's just sort of tricky. So I'm going to switch over and show you something on my paper so you don't have the frustration that I had when I answered this question the first time. You have seen me, so you know that I sometimes read and make assumptions and answer too quickly. But that's what makes a problem in this one. Do you see how this is 0.29%? So if you want to subtract that to 1 to find the complement, you have to first change this to a decimal, which is 0.0029. In other words, not that many women out there with color blindness. If you got it, you are exceptional, right? Because you are doing something that's very unusual. So you have to change this. And so then I'm going to take 1 minus 0.0029 and I'm going to get 0.9971. And it says type it in exact form, so you would do that, 0.9971. Common mistake, 1 minus 0.29. That's what I did, but that doesn't make sense. It's not 29%, it's 0.29%. It's a very unusual occurrence to have color blindness, especially for women. The following data results suggest from 956 pedestrian deaths that were caused by accidents. If one of the pedestrian deaths is randomly selected, find the probability that the pedestrian was intoxicated or the driver was intoxicated. So they already told us what our sample space totaled up to. I'm not going to have to do that. I got to tell you this funny story. You can fast forward. I'll sit like this while I tell it. Fast forward until I'm not doing this anymore if you don't want to hear it. So when I was a kid, we were doing a contest at school, and you were supposed to turn in 20 words or less what you want to do when you grow up, and then you could win a scholarship. So I was really terrible speller, so I decided I wanted to be a pediatrician. And so I went to my mom and said, how do you spell pediatrician? And she said, what my mom always used to say was, look it up in the dictionary. Well, I always found that weird, because if you don't know how to spell it, hard to look it up. But anyway, I went and looked it up, and I looked up pedestrian, but I thought that looked pretty good, like pediatrician. So I wrote down I want to be a pediatrician when I grow up because I want to help people, whatever. I want to be a pedestrian when I grow up is what I wrote because I want to help kids or whatever. And it wasn't until I sent my thing off for my scholarship thing that my mom actually read my card and she started dying laughing. What, you want to be a pedestrian when you grow up? And so to this day, my family will sometimes, you know, we're taking a walk and they're like, man, you really reached your goal. You know, you became a pedestrian. So that's my poor spelling thing. Whenever I see the word pedestrian, can't help but think about that. Okay, done. Okay, so anyway, if one of the pedestrian deaths is randomly selected, find the probability that the pedestrian was intoxicated or the driver was intoxicated. Okay, here's the pedestrian intoxicated people here. So the chances that the pedestrian was intoxicated are right here. We're going to add these two together to get that total, which is 358. So we have 358 chances that the pedestrian was intoxicated. I'm going to call that pedestrian intoxicated. But because they said or, that's an addition problem. We also want to say or maybe the other driver was intoxicated. So we want to add up the driver being intoxicated. Now if we add up the driver being intoxicated, we would get 132 across here. But we already counted these people, and you don't want to double count. I should have talked about that in the notes so that you can kind of see there's a different way to think about it. But what I'm going to say is since I already counted these 81 people, I'm only going to count these 51 people. So this total across the way was 132, but I didn't put 132 in because that would have been double counting the 81 that I counted in the first place. So now if I add up the 358 and the 51, I get 409 out of 956. And I get 40 to 3 decimal places. I get 0.428. 0.428 probability of getting somebody who was one or the other. Remember, don't double count. That's the big lesson to be drawn there. Okay, 7. Where's 8, 9? Oh, there was. I still have that one. Okay, sorry, my pages get all wonky with 8, 9, around 10, 11. Okay, let's see what page 12 has to offer. Yikes, there's a lot to answer on page 12. Let's see what they got here. This number 19, the following data lists the number of correct and wrong dosage amounts calculated by 34 physicians. Well, that's frightening. In a research experiment, a group of 19 physicians were given bottles of epinephrine labeled with a concentration of 1 milligram in 1 milliliter solution, and another group of 15 physicians were given bottles labeled with a ratio of 1 milliliter in 1 to 1,000 solution. Complete parts A through C below. The concentration in dosage, if the correct dosage calculation would be 14, the wrong dosage calculation 5. If they were labeled this way, they got the correct dosage twice, but they 13 times screwed it up. So we can look at these and say, this one seems to be harder for them to deal with, right? So this would be a better way to package that medication so we don't get so many people messing up. But even 5 and 19 seems pretty bad to me. Okay. For the physicians given the bottles labeled with the concentration, find the percentage of correct dosage calculations and express it as a possibility. So for that, you're going to find the percentage of correct dosage calculations by the correct ones were 16, right? And we had a total 34, right? 27, yeah, 26 out of 34, and you're going to round it to 3 places. For the physicians given the bottle labeled with the ratio, find the percentage of correct dosage calculations. What did I just do? Label with a concentration. For the physicians given a bottle labeled with the ratio, oh, I see. One of them was given the ratio, right? So I did this wrong. So the physicians given the bottle labeled with the concentration, sorry, this is the concentration. There were 19 of them, and the probability that they got it right was 14 out of 19. For the physicians given with a ratio, which was the second one, there were 15 of them, and the correct ones were 2. We're going to round those to 3 places. Does it appear that either group did better? Well, obviously, the one that had 2 15ths were doing pretty bad on getting it right. So the groups given with the concentration that actually did better, right? They had fewer mistakes. The probability of a correct dosage calculation for the bottles labeled with the concentration is much. The concentration is when they did better. The probability is much greater of getting the probability of a correct dosage than those with the ratio. So you want to, I guess you want to do the concentration, not the ratio, if you don't want people to die all the time from incorrect medications, which is a really common mistake in hospitals and a common problem out there. You probably, there's a good chance that you know somebody who had that happen to them. Most of us do, because not that they died from it, not everybody dies, but what I'm saying is it happens and people get sick or whatever from it. Okay, the results suggest that the label does not affect it. The labels with ratios are better than the concentrations, or the labels with constant. Well, that's pretty obvious. You want ones that give people the right answer. Okay. Pollsters are concerned about declining levels of cooperation amongst people contacted in surveys. A pollster contacts 86 people in this age bracket and finds 58 of them respond and 28 refuse to respond. When 277 people in that age group they have that many people that way. Suppose that one of the 363 people is randomly selected. Find the probability someone in the 18 to 21 age bracket. Find the probability of getting someone in the 18 to 21 age bracket or someone who responded. Okay, well, we can see the answer there, but let's do this. Okay, so we have 18 to 21 age bracket, and we have 22 to 29 age bracket. The responded people for 18 to 21, 58 of them respond and 28 refuse. For the 22 people, there were 235 who responded and 42 refused to respond. Okay, so they say suppose that one of these 363 people, so 363 is our sample space. That's the total. Suppose that they answer, what's the probability that someone is in the 18 to 21 bracket or responded? Well, 18 to 21 was 86 people. So 86 people are in that. That's one of the possibilities. The or tells us we're adding. So or they were responding. So then we have these people that responded, but be careful because we already used the 58, right? So we used the 58 when we added them in here. So this is the overlap. You don't want to include an overlap. So you'd have the 28 people, the 58 people, and the 235 people. And then if I add 235 and 86, I get 321 divided by 363, and I'm hoping that that turns out to be 88.4, which it does when I round it off, approximately, right? 0.884. So you have, I did it in a chart so it could make sense to me. You may not need to do that, but that kind of is how I would do it. And then remember that we don't want to count people twice, so we're just looking at that. And the way the book or other things will say to do is they say do the 86 that were 18 to 21, then you add on the 58 plus 235, which is 293, and then you subtract off the overlap. And that's another way to get to the same answer, 321 over 363. But instead of doing that, I just don't add that overlap in the first place. Instead of taking it off on the end, I'm like, oh, I'm not counting that again because I already did. But that's going to get you the same way. So if you do it that other way, that's fine as well. Okay, that was 20. Yay, we're almost done. 21. I think this probability is kind of fun, but I will say that people find the probability section challenging. Hopefully you're not, because I've explained it so perfectly that it's easy for you. But okay, use the following results for the test for marijuana use, which is provided by a certain drug testing company. Among 144 subjects with positive test results, there are 23 false positives. Among 150 negative results, there are 4 false negatives. How many subjects were included in the study? I don't know. I can't tell. So there was positive and negative. So I'm going to do that. Positive and negative results. And there were, I'm going to say true and false. False positive, false negative. Okay. 144 subjects with positive test results. 23, so this is the positive test results column. 23 were false positive. And I know there was 144 altogether. So I'm going to take 144 and subtract the 23, which means I had 121 people who had positive results who truly did smoke pot. Okay, and then among the 150 negative results, so there's a total of 150, there are 4 false negatives. So false negatives were 4 out of 150, which is 146 then. Okay, so how many, hint, construct the table. No, okay, so how many subjects were included? There was 144 here and 150 here, which means there was a total of 194 subjects total. Okay, that part should make sense to you. Whoops, no, not 100, 294. Just checking the answer. Yeah, I didn't add correctly. So up here, it's 294 people. How many subjects did not use marijuana? Okay, negative, the negative people who weren't using marijuana. Well, see how there was 150 here, but only 146 were really using. So I'm going to say there was 146 people from this column who actually did use it. Oh, wait a second. No. Here, wait a second. How many subjects did not use marijuana? There was 146 people that truly did not use it. They were negative and truly they didn't use it. That is what I wanted to write. And over here, there were 26 more people who were accused of it that really didn't. So the people who really didn't were 169 people that did not use marijuana. Those are the people that were falsely accused and the people that were actually didn't. You know, that's where I get that 169. What is the probability that a randomly selected subject did not use marijuana? Well, 169 we just said did not use, and 294 we said was our total. So 169 divided by 294 is how we get the 0.575. You can check that on your calculator. About 0.575 rounded to 3 places. Okay. Those little charts are helpful, but it is confusing. I get confused on that. I don't know why that one and the intoxication pedestrian one, I can get confused. I really have to make a chart for that. Okay. Use the following results from the test for marijuana use, which is provided by a certain drug testing company. Among 141 subjects with positive results, 23 positive, false positives, and 3 false negatives. If one of the test subjects is randomly selected, find the probability of a false positive or a false negative. So we want to know how many people were tested altogether. There was 141 and 160, so we had 301 people that were tested. We were looking for the sum of those two things, the false positives, which was 23, and the false negatives, which were 3. What this is telling us is how many times was the test wrong, right? So that's why we're talking about the test's accuracy right here. Anyway, 26 divided by 301 is that number there, 0.086 approximately, 3 decimal places. And with an error rate of 0.086, the test does not appear to be highly accurate, or it does appear to be highly accurate. We're talking about 5% as our cutoff. If it's more than wrong, it's wrong more than 5% of the time. I don't like it. This is not good. This means that 9 out of 100 people are going to be falsely tested. That's not that accurate. So I would say not a good test. I'll let you answer that one on your own. Okay. Number 23. Describe what the probability of B/A represents. The probability, this is a oh my gosh. You ever gone to say a word and it's just gone from your head? That's conditional probability. I could say it. This means that this is the probability that B occurs given that A has definitely occurred. So if we wanted to say, what's the probability that a woman has blonde hair? We're saying, what's the probability of blonde hair given that it's a woman? We already know we're looking at women, and then from there we look at the ones with blonde hair or something like that. So it's the probability of event B occurring when we know that A has already occurred. So this is it, the probability of event B occurring given that event A has already occurred. That's that conditional probability. We know that this can happen based on the fact that this other thing has already happened. Okay. For the given pair of events, A and B, complete parts A through B below. A, when a page is randomly selected and ripped from a 7-page document and destroyed, it is page 7. What's the question? Okay. A, determine whether events A and B are independent or dependent. If two events are technically dependent, can be treated if they are independent according to the 5% guideline. Da, 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 da. Okay. If you do something like, let's say you take a playing card out of a deck of cards. There's 52 cards in a deck. If you take out one card and then you go to draw the second card out, you have changed the outcome of the second thing because you've changed the deck. Okay. But if you had 750 cards and you took one out and then you went to draw the second card, you really, you have technically changed it, but the chances are so low because there's so many cards in there that we sometimes say those events are independent because that 5% thing, has less than a 5% effect, then it's no big deal, right? That's kind of what they're talking about. So when you take, let's say you're taking assembly line and you produce, let's say 10,000 items in a day, and you randomly select an item every few minutes off of there to look at them to see if are they defective. You don't put them back in. If it's defective, you don't put it back in. So you've chosen, let's say, 16 items throughout the day out of 10,000. You would consider those independent because it's such a small percentage of 10,000 that we consider them independent. That's what that 5% guideline is talking about. But anyway, this one's only got 7 pages. So a page is randomly selected and ripped from a 7-page document and destroyed. It's page 7. When a different page is randomly selected and ripped from the document, it is page 1. Now, let's see what they're asking here because I really don't, I'm not fully sure what the question is. If you rip it out, to my knowledge, then it's gone. And you have definitely altered what's happening the next time, right? Because now there's only 6 pages left. You rip one out, you have a lot less chances. You've limited your options greatly for that second thing. So the two events to me are dependent. Because the occurrence of one, no, I don't like that one. The two events are dependent because the occurrence of one affects the probability of the occurrence of the other. If you take out one page out of 7 and then you go to select a second page, well, you've changed things because now there's missing a page, right? So I would say D, big time. The probability that events A and B both occur is, and then we have to figure that out. Well, the probability that you go in there and pull out page 7 out of 7 pages, that's 1 out of 7 pages that you have, right? You chose one page to rip out of 7 that were there. But now, for your second page that you're ripping out, that's why you're ripping it out, I don't know. But now there's only 6 pages left. That's how we know the first one affected the second one, because you've changed it, right? And now we're taking out 1 again, though. We're taking out 1 page out of 6. So that looks like 1/42 to me. and that's 0.238 approximately. Whoops, sorry, 0, 2, 4. This one they wanted 4 places out. Okay, 2, 3, 8. Okay, so when you're doing something one after the other like that, if you were to pull out yet another page, you would be down to 1/5, and another page 1/4, right? Because each time you're losing a page. So they are dependent because one affects the other. What would be independent events? Like, let's say that I had a deck of cards and I drew a card out and I looked at it and I got the Queen of Hearts, put it back in, shuffled, and now I'm going to draw again. Well, I put that first card back in. So I haven't changed. There's still 52 cards in my deck. Those are independent because I didn't alter the second draw because I replaced what I took out in the first draw. Okay, that's independent. This one, dependent. Okay. For a given pair of events A and B, okay, a marble is randomly selected from a bag containing 10 marbles consisting of 1 red, 3 blue, 6 green. The selected marble is one of the green marbles. B, a second marble is selected and it is one of the red, it is the red marble in the bag. Determine whether they are independent or dependent. Well, the thing that's bugging me about these problems is they don't say did they put the marble back in, so I'm assuming they didn't, but they really should say they didn't replace it. But anyway, the two events are dependent because when you change the number of marbles in the bag, you've changed things, right? Because that affects one affects the other. So that's this one. They are dependent. You took out a marble, you change things, right? If you put it back in, then they could be independent. The probability that events A and B both occur. Well, when you start off, you have 10 marbles in your bag. And you were going to draw a green one, and there's 6 green ones. So you have 6 out of 10 chance of drawing a green marble. Okay? That's the probability of the first draw. Now, when you go back in, you didn't put that marble back. So there's only 9 marbles in your bag. And you want to draw what? It's a red one. 1 red, so you have 1 out of 9 chances of getting that. So you have 6 over 90, or somebody's at my door. Okay, hang on, let me pause and I'll be right back. Okay, so I'm sorry, I don't know how long that felt to you. It was quite a while actually. Okay, so 6 over 90 is 1/15, which is 0.0667 rounded to 4 places. I don't really get why. Sometimes it's 3 places, sometimes it's 4 places. Seems random. It seems random to me too. But anyway, that's what they're asking for, so we're going to go with that. Last question. Dun, 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 dun. Number 26. Refer to the table below. Here's a bunch of blood types. I think this is one that I put on the midterm and final. I kind of like this question, I think. Maybe I don't. I think I do, though. Okay, given that 2 of the 108 subjects are randomly selected, complete parts A and B. Assume that the selections are made with replacement. We pick somebody out of the group, we put them back in. Ah, that means that it's 108 people every time, right? Because I put them back in. Assume that the selection made with replacement. What is the probability that 2 selected groups are both group O and type RH+? Okay, so that the 2 selected subjects are both group O and RH+. So we select the first person, and there's 108 people in my sample, and I want them to be O and RH positive. Well, here's my O column, and here's my RH positive column. So there's 41 chance out of 108 that I have 41 people that are O and RH positive. But that's my first person. My second person, I'm going to go back, but I put that first person back in, so I have 108 people again, and I've got the same probability twice. 41 over 108, which I would just do this. Put a fraction into your calculator if you've bought one of these cool ones that I've been trying to get you to buy. 41 over 108, and then take that to the second power, and that gives me 0.1441. I should always do an equal, but then we round off, so I'm saying approximately 0.1441. Yay. Okay. Assume the selections are made without replacement. Pretty similar. What is the probability that they are O and RH positive? Without replacement, I have this first person, 41 times out of 108. And then my second one, well, I didn't put that person back in. So I got 107 people in my pot. And I took one of these people out, which means I only have 40 left. So I have 41 people out of 108 the first time, but now I've reduced each of those things by 1, and so I need to multiply 41 over 108 times 40 over 107. And that gives me 0.1419, approximately 0.1419. And that is the first chapter on probability. Out of 2, it's not a huge part. We need to do probability because we need probability to understand some of the stuff that we're doing in the later chapters. So it's statistics and probability, because you really can't talk about inferential statistics without talking about a little bit of probability. Okay, I will see you next time. Have a fantastic